surrounding surfaces. As the gas escapes through a rear outlet, it creates a forward thrust on the rocket. And here we have Sputnik 1, the first satellite, 4th of October 1957. And here is a diagram of the 3-stage rocket for satellite launching. So it starts at the top, artificial Earth satellite, and this section, engine for 3rd stage, solid fuel. This section, compressed gas. Here we have the fuel tank, oxygen tank, engine for 2nd stage, fuel tank, hydrogen peroxide for driving the turbine, oxygen tank, pumps, and engine for 1st stage. Now, this book has a date of 1964. Storybook Spaceflight. Although we think of rockets and space travel as very new, men have dreamed for centuries about flying. They longed to soar and glide with the ease and grace of the seagull and the swallow. A Greek writer, nearly 2,000 years ago, wrote about a ship which was caught in a water spout and carried up to the moon. Later he described how another daring explorer made a pair of wings and set out upon a voyage to the moon from the top of Mount Olympus, the house of the old Greek gods. For a long time after this, we do not find much about journeys into space. Then the telescope was invented, and men began to learn more about the sky. A famous astronomer named Kepler discovered the laws which control the movements of the planets, and he wrote a book telling about a voyage to the moon. Kepler's hero travelled there by the simplest way of all, by magic. He knew that there was no air between the Earth and the moon, and could think of no other way of getting there. In 1638, a bishop named Francis Godwin told of a traveller who was carried to the moon by 10 wild swans. I think this is it here. Yeah, the flight of the wild swans. A strange flight which you can see in the picture opposite. A French author, Jules Verne, who lived 100 years ago, wrote a book entitled From the Earth to the Moon. His Voyager was fired from a great gun, but Jules Verne forgot 2 very important things. His traveller would have been killed by the explosion, or roasted by the heat produced as the great shell rushed through the air. Fireworks and weapons. The first rockets fired by gunpowder were made over 700 years ago by the Chinese. They were simply fireworks, just like the Guy Fawkes rockets which light up our skies every year on November the 5th. Rockets were later used for carrying lifelines to rescue sailors from wrecks or from the water. Some people thought rockets might be used in place of guns in time of war, but it was found that guns were far more accurate than any rocket which could then be made. After the War of 1914 to 18, a new interest was taken in development of rockets. The chief reason for this was that men had now learned how to fly, but spaceflight is very different from flying an aeroplane. An aircraft must have oxygen to burn its fuel and provide power to drive it. Air must flow over and under its wings to support it. How could anything hope to fly without air? The foundations of rocket flight was laid by a Romanian scientist and mathematician, Hermann Oberth. of the sun's gravity. If it acted alone, this would pull all the planets into its vast furnace, where they would melt like snowflakes. The other force is one which comes from their movement. This tends to throw them out into space like a stone which is being swung around on the end of a string. These two forces just balance. If a satellite is launched at a high speed, it may go far away from the Earth and be lost. If the speed is not high enough, it will fall back and be burned up as it rushes through the air. If we want the satellite to travel around the Earth, it must be sent at the right speed, and this varies according to the distance of the orbit from the surface of the Earth. If we wanted to travel round at a height of 200 miles, it must have a speed of about 18,000 miles an hour. At this speed, it can go on travelling around the Earth for many years. And here is a satellite's orbit around the Earth. Space rockets are big. Scientists in America who are planning to explore space may build a rocket which will stand as high as a tall building, like St. Paul's Cathedral. Why is it necessary for rockets to be so large when it is much harder to lift a heavy weight than a lighter one? The rocket which carried the American astronaut Colonel John Glenn into his orbit round the world weighed 120 tons and was 80 feet high as it stood on the launching pad at Cape Kennedy, formerly Cape Canaveral. But the most important part of the rocket, the capsule in which the astronaut travelled, held all the delicate instruments, radio, oxygen and safety equipment, and weighed only a small fraction of the total, not more than 1.5 tons. This part of the rocket is known as the payload. The rest of the weight was taken up almost entirely by fuel. The fuel and the material which supplied the oxygen to burn it made up over 100 tons of the total weight, while the rocket itself weighed no more than 12 tons. is now in a strange state of weightlessness. If his spacecraft was large enough and he was not strapped down, he would float about like a thistledown. To move about, he would have to pull himself hand over hand along a wall or kick against a wall, in which case he would move away in a straight line until he hit the opposite side. Eating and drinking would bring some tricky problems. It would be impossible to pour a liquid down your throat. Your pen or pencil would float away from you if you let it go. This is inside the capsule. Return to Earth. There is no reason why a spacecraft in orbit should not continue travelling around the Earth for a very long time, since there is nothing to upset the balance of the forces which keep it in place. A man who is shut up inside such a small space with only a limited amount of air, water and food could not stay alive for very long in those conditions. Apart from the strain on his body, there is a very great strain on his mind. Space is very large and very lonely. Sooner or later he must be brought down to Earth. This is one of the most difficult problems which the space scientists have had to solve. The hardest part is sometimes called the re-entry problem. It is not difficult to reduce the speed of the spaceship and allow the Earth's pull to take effect. The important thing is to make sure that this happens gradually. If the Earth pulls it back unhindered, the speed of its fall through the air will make it so hot that the craft will burn up like a shooting star. First, the spacecraft must spiral slowly towards the Earth by firing the retro rockets to check the speed. As it enters the atmosphere, a parachute is released, and this enables the astronaut to make a safe landing. Hoping that if all has gone according to plan, there are ships and aircraft to transport him safely back home to tell of his great adventures in space. This is Rescue from the Sea. Journey to the Moon. Some people think it is a waste of time and money to send a manned spacecraft to the moon, but this argument has been used about many other ventures, like the first aeroplane or the voyage of Columbus. Men are always eager to find out more about the worlds around them, and we cannot be sure just which experiments are going to prove useful until we try them. Until recently, men thought of the moon as something very beautiful to look at, but quite beyond reach. Crying for the moon has always meant asking for something which can never be ours. Now this idea is changing, for a spacecraft sent from Russia has travelled round the moon and taken photographs of the far side, which is always turned away from us, and other rockets have landed on the surface very close to the target areas. Already we know a great deal about the moon from the use of telescopes and other instruments. It is a world of great extremes of temperature. When the sun is high in the sky, the moon's surface becomes as hot as boiling water. At night it is frozen in intense cold. There is no air, and it seems unlikely that any life exists on the moon. stand still because the Earth's gravity would pull it down. It would have to revolve around the Earth, just like the Moon or an artificial satellite. One suggestion is that it should be shaped like a wheel, about 250 feet in diameter. Another kind of platform in space was proposed by an Austrian engineer. It was to revolve much farther away from the Earth, at over 20,000 miles, where its speed would just match the speed of the Earth's rotation. This would make it appear in a fixed position above one part of the Earth, like a star which always remains overhead. There are very many difficult problems connected with the building of space platforms of this kind, especially if they are designed to be occupied by human beings for periods of weeks or months. It seems very likely that the fully equipped space station is something which lies in the distant future. A smaller unmanned satellite will probably serve many of our purposes for a long time to come. And here we have a possible space station in orbit. Okay, so I am going to leave my reading there, and we will continue with this lovely book from 1964 about exploring space in another video. This has been Kate at the Library of Whispers. Thank you so much for joining me, and I shall see you very soon. Bye bye for now. Bye bye. Hello everybody, this is Kate at the Library of Whispers, and today I'm going to read the second part of this lovely Ladybird Achievements book. It's titled Exploring Space. So let's find the place that I was up to. Target: the Moon. Let us suppose that we are aboard a rocket ship bound for the Moon. It is a journey that would take about 3 or 4 days, and as our rocket roars into the sky, we watch the land and sea falling behind us. The clouds, too, are soon left behind, and the sky becomes a darker blue. The curve of the Earth is clearly visible from 100 miles above its surface, and after a day's journey, our planet becomes a distant globe, like a big full moon. It is a water blue colour and streaked with patches of cloud, beneath which we can see areas of green and brown where the forest and desert lands are found. At the north and south poles are the white ice caps. The pull of the Earth's gravity is weakened, and the feebler pull of the Moon is growing as we approach. There is a blaze of sunshine, far more intense than we find on Earth, but in the shadows, when the sun is not dazzling us, the brilliant stars shine out in a sky of velvet black. We are falling at a speed of 5,000 miles an hour towards a strange world of dusty plains, rugged mountains and great craters, which has remained almost unchanged for millions of years. Our landing is controlled by a radar set in the rocket ship, which can judge our distance accurately. At the critical moment, the forward-firing jets begin to blaze. We are feeling our own weight again as the engines reduce our speed. For a few seconds, there is a cloud of fire and dust, and then silence. We are on the Moon. So this is the rocket ship that people in the early 1960s assumed was going to land on the Moon. This is the bit that's leaving the Moon. visible for much longer, and they could be seen even in the daytime. There would be no sunlight to dim their brilliance, as happens in the bright blue skies we see above the Earth. Of course, lunar explorers will have to eat and breathe. Oxygen must be provided to keep them alive, but not all the oxygen on the Earth is found in our atmosphere. There is much in the rocks too, although it is mixed with other things. It may exist in the rocks on the moon. Crops could be grown on the moon in specially sealed greenhouses, feeding on minerals dissolved in water. They would have 14 days of continuous sunlight to help them grow. Getting away from the moon would be much easier than getting away from the Earth. Because of its smaller mass, the moon's gravity pull is only a small fraction of that exerted by the Earth. And this picture is exploring the craters of the moon. How much do we weigh? You have probably read about Sir Isaac Newton and how he saw a falling apple and linked it up with the worlds in space through the law of gravity. This acts as though the Earth were a great magnet which pulls things towards it. But we must think of the magnet as though it were not on the surface of the Earth where we live, but buried deep at the centre, 4,000 miles beneath our feet. Since the Earth is not quite a sphere, but bulges round the equator and is slightly flattened at the poles, we are farther from the magnet at the equator than we are at the poles, and so we weigh a little less on the equator. If we get 4,000 miles from the Earth's surface, a pound weight would weigh only 4 ounces. A man who weighs 12 stones would weigh only 3 stones at the same distance. On the moon, where the gravity pull is only 1/6 of that of the Earth, our 12-stone man would weigh no more than 2 stones. As we have already seen, the space traveller who is going up in a rocket will weigh 3 or 4 times more than normal. The exact increase depending on the speed of the rocket and how quickly it is accelerating. The men who have circled the Earth in a spacecraft have first experienced this great increase in weight, and then the complete opposite. Once in orbit, they become weightless because the speed of their spacecraft as it circles the Earth tends to throw them outwards, and this just cancels out the pull of the Earth's gravity. This is an astronaut floats without weight. Looks like something from Buck Rogers, doesn't it? The planets near the Sun. The nearest world to the Sun is the little planet Mercury. It is not much bigger than our moon, and very few people have seen it, although it shines quite brightly in the sky at certain times. In the British Isles and other northern countries, it is best seen during the weeks of spring, when it comes for a few evenings into the western sky after sunset. It is always up there in the sky, somewhere near the Sun, but we can only see it when the Sun is below the horizon and the planet is at its greatest distance from the dazzling sunshine. Mercury travels round the Sun every 88 days. It turns the same face towards the Sun always, and for this reason it is intensely hot on that side. On the other side, strangely, where there is endless night, it is the coldest world of the solar system. Mercury would be a very unfriendly world for space travellers. Venus is a much larger planet, very much like the Earth in size, but there are many mysteries about it. It shines very brightly in the night sky, or in the early morning sky before sunrise. guess these will soon be followed by others. We have great hopes that one day we shall know what kind of a world this beautiful but mysterious planet really is. And this picture is Little Mercury, the hottest and coldest world. The outer planets. Beyond the orbit of our planet Earth lies the red world of Mars. It is the only planet of which we can clearly see the solid surface. When it comes into our night skies, it shines with a bright orange-red light. Through a telescope, we see the orange-red globe marked by patches and streaks of a blue-green colour. These dark patches may be some kind of plant life. The narrow streaks are the famous canals. What they really are is one of the most fascinating things which the spacecraft of the future may be able to tell us. Outside the path of Mars are the two giant planets, Jupiter and Saturn. They are both very cold worlds, and though very beautiful to look at, they are surrounded by dense atmospheres of poisonous gases. Although we cannot think of Jupiter with its 12 moons and Saturn with its splendid rings as likely homes for living creatures like ourselves, the spacecraft equipped with instruments will doubtless one day tell us much more about them. Far beyond Saturn are the other two giant worlds, Uranus and Neptune, about which we know very little as yet. They are so far from the sun that its feeble rays cannot give them much warmth, and they could not possibly support living things like those we know on Earth. At the outermost edge of the sun's kingdom is the little world called Pluto, much smaller even than the Earth and 3,600 million miles from the sun. Beyond Pluto there is only empty space and the stars. And here, this picture is the red planet Mars, a world where life may exist. Out to the stars. The sun is the nearest star. It seems so very much bigger and brighter than all the others, only because it is so much closer. Other than the sun, the nearest star is to be found in a constellation called the Centaur. Unfortunately, if we live in the northern part of the world, we cannot see this constellation as it lies in the southern hemisphere of the sky. The name of the star is Proxima Centauri. Even Proxima Centauri is separated from us by many millions of miles. The swiftest traveller we know is a ray of light, but light speeding at 186,000 miles a second takes over 4 years to reach us from this star. It would be a very long journey, even if our spacecraft could travel at the speed of light. Most of the stars we see in the heavens are far more distant. The brightest one in the whole sky is called Sirius, the dog star, and it is also nearer than most. Its light takes just over 8 years to travel to the Earth. Some of the stars are so far away that the light rays must travel for many centuries across the vast space which separates them from us. No manned spacecraft from Earth is ever likely to travel so far or so fast. Oddly enough, however, it would take very little more energy to send a spacecraft to a star than it would to one of the planets. And here is an imagined spacecraft in flight. has steadily grown, and we are now beginning to realise that the artificial satellite is capable of doing much useful work. If we want to send a radio message to a country on the other side of the world, the problem is complicated by the Earth's round shape. Radio waves, like light waves, travel in straight lines. To send radio waves round the world is like trying to see round a corner. Sometimes at a street corner you may have seen a large mirror set up to show drivers and pedestrians if anything is coming from another direction. This is one way of seeing round a corner. Radio waves too will bounce off certain things and change their direction. High up in the Earth's atmosphere is a layer of air which will make some radio waves do this, and so a message can be sent around the world. This layer of air deflects the waves back to Earth and prevents them going straight out into space. At certain times, however, this layer of air may be upset and fail to work properly. It frequently happens, for example, when there are many spots visible on the surface of the Sun. A satellite which is high above the Earth can be used to bounce radio waves back to another part of the world. Unlike the layer of air which does this, the satellite is not disturbed by sunspots, and so it always works well. Television pictures are now sent over long distances by the same method. And here we have a satellite shaped like some strange creature from another world. Watching our weather. From its lofty position 100 miles or more above the Earth, the satellite can keep a close watch upon the atmosphere and the cloud formations which cause our weather. The Tyros satellite was most helpful in tracking the fierce storms known as typhoons, which could not be forecast by other means. One of these moons, Tyros 3, found over 50 of the great storms and tracked them from the beginning to their end. Satellites do not mean the end of weather stations on the is greatly magnified and makes the view of a star or planet very unsteady. The twinkling of a star is caused by the same thing. It makes clear, sharp views of the moon, planets and stars impossible. This is the reason why some astronomers and scientists are hoping that a fairly large telescope may be sent into space above the thick lower layers of the atmosphere. Already, telescopes have been sent up to a great height in balloons, and even in this way, the photographs which have been taken with them have shown that the upper air is much clearer than the dense layers near the ground. When a telescope can be sent into space above the air, it will have a better chance of taking clear photographs of the sun, moon, planets and stars. Many scientists think that this would be a much better plan than taking all the trouble needed to send a man into space. And here we have taking pictures by telescope and camera suspended from a high altitude balloon. Life on other worlds. We have already seen that the planet Mars may possibly have some kind of plant life. Some people thought that intelligent beings lived there too, and had built canals to carry water from the melting snows of the polar regions to the dry desert parts of the planet. Although this was a most interesting idea, it is unlikely to be true. Regarding the possibility of life on the other planets, Mercury is too hot on one side and too cold on the other, and it has no atmosphere. We know little of Venus, but apart from Mars, all the other planets seem certain to be far too cold for life. What can we say about other stars? The stars themselves are very hot bodies like the sun, and nothing could live on them. There may, however, be some which have planets like those which travel round our sun. An American astronomer has said that one of the nearest stars certainly has a large planet bigger than Jupiter revolving round it. In our great Milky Way system, or galaxy, there are about 100,000 million suns. If we suppose that planets are very rare, belonging only to 1 in a million stars, it seems that there could still be many thousands of planets. Some of these might have life like that of our own world. It is also possible, of course, that in other parts of the universe there may be living things quite unlike us. One thing we do know is that the materials of which our world is made, the elements as they are called, seem to be much the same in every part of the universe. And here is the Milky Way. And that is the end of this book, although there is a little bit at the back. So let's read this. Signposts to space. There are no fixed distances in space, as everything is moving. The figures given below are approximate distances for each planet. The figure given is when the Earth and planet make their nearest approach to one another. However, a rocket travelling to a planet must follow a curved Proxima Centauri, and its light takes just over 4 years to reach us, travelling at about 186,000 miles a second. A light year, the unit we use to measure distances to the stars, is 6 million miles. And that ends that lovely exploring space book. I hope you enjoyed it. This has been Kate at the Library of Whispers saying, I shall see you very soon. Bye bye for now. Bye bye. Hello everybody. This is Kate at the Library of Whispers. Now, as promised, I'm going to read this lovely Ladybird book. It's called How It Works, The Rocket. It's a bit of a request in a way, because somebody pointed out, quite rightly, that I haven't done any sciencey based reading for a while, and that is true. So I'm going to try and rectify that by starting with The Rocket today. Now this is one of my vintage Ladybird books. You may be familiar with those now. Let's have a look inside. Now this one is in quite good condition. It's from 1967. You can see how old it is with these lovely pictures. Introduction. Space travel is often in the news. Many films and stories have been written around this intensely interesting subject, but none of these captured our attention more than the actual facts of man's historic landing on the moon on the 20th of July, 1969. His successful escape from the moon's gravitational pull and subsequent safe return to Earth were equally stirring. Space stories we see on the screen or read in books are sometimes based on fact, but the imagination of the authors is used to add fiction to fact and make the tales as exciting as possible. But what really happens when a rocket is launched? How is it propelled? How does it travel in the emptiness of space? Why do space vehicles stay in orbit around the Earth when their store of propellant has been used up? These and many other fascinating questions are answered in the following pages of this book. Not all rockets are used as space vehicles. Several other uses are also described. There are 2 other Ladybird books, which will provide more information for boys and girls of all ages who have an interest in aeronautics and astronautics. These are How It Works, The Aeroplane, less lift for the wings and less oxygen for the engines. At 20 miles above the Earth, an aeroplane reaches its absolute ceiling because there is just not enough air for it to operate. It is obvious, therefore, that no aeroplane will ever fly in space, let alone reach the moon. This brings us to the essential difference between the aeroplane and the rocket. Rockets do not need air. They travel better above the atmosphere, where the air is so thin it offers little drag or resistance to forward and upward motion. The oxygen needed to operate the rocket's motor is carried in a tank built into the rocket itself. Once the Earth's gravitational pull has been overcome, the rocket will continue on its chosen path without further propulsion. And in this picture we can see the limitations of an aircraft compared with a rocket. First principles of rocket propulsion. When you walk upstairs, you do so by pushing down with your foot on each step. When you climb a rope or a tree, you lift your body upward by pulling downward with your hands. In fact, to move in any direction, you have to exert pressure in the opposite direction. The movement in the one direction is exactly equal to the pressure in the other. To express this principle in its correct form, we say that to every action there is an equal and opposite reaction. Newton's third law of motion. When a rifle or any sort of gun is fired, there is a sharp recoil or kickback after firing. This is the backward reaction of the gun to the forward action of the bullet or shell leaving the barrel at high speed. Now, if the gun were pointed toward the ground and fired, the recoil would be in an upward direction. That is very roughly how a rocket works, except that instead of a bullet leaving a barrel, edges of the metal, lower drawing. The gases will escape through the opening and the balance of the forces in the container will be upset. The gases will escape freely through the exhaust and the upper portion will have an unbalanced upward force which will therefore move the entire container upward. This upward force is equal to the force of the gases escaping downward through the opening. In a rocket, there is a combustion chamber which works in just the same way as the open-ended container. And of course, this is a diagram of the reaction principle of a rocket. Propellant storage tanks. It has now been clearly established that a rocket's upward or forward motion is made possible by hot exhaust gases escaping at high speed through the opening at the rear. These gases are created by burning special propellants inside the rocket. Large tanks are built into the rocket to carry the propellants. In fact, these tanks are the largest parts in the rocket's structure, and the weight of a propellant they contain is often as much as 90% of the weight of the whole vehicle before it is launched. It is therefore necessary to use the kind of propellants that will give the greatest thrust for their weight and the amount of space they take up. In other words, they must be as efficient as possible. Similarly, the tanks themselves must provide a maximum capacity with minimum weight. A thin rocket will create less drag than a fat one as it travels up through the Earth's atmosphere, so the tanks must take up as little sideways space as possible. To save unnecessary weight, the tank sides have to be very thin. This means that a strong material is required. Some types of tank are built separately and then fitted into the rocket tube. Another kind is built as part of the main structure, the sides of the rocket actually forming part of the tank. This design saves weight because the one section of material does two jobs. Tanks are sometimes made to fit round the outside of the rocket so that they can be jettisoned when they are empty, and their useless weight doesn't have to be carried any higher than necessary. And in the illustration we have a rhombus rocket with jettisonable tanks and a diagram of a fuel tank fitted into a rocket tube. Types of propellant. Every Gladstone rocket with Mercury spacecraft. The propellant pumps. From the previous chapter we know that most large rockets use two liquid propellants, each stored in a separate tank. But before the rocket can function, these propellants have to be fed into the combustion chamber and ignited. The first items in the fuel feed system are the pumps. These are located below the tanks, and their job is to pump the propellants from the tanks through control valves and injectors into the combustion chamber. A pump consists of a bladed wheel known as a turbine, which is driven by chemically produced high-temperature steam. It is mounted between two turbo impellers. These are metal discs fitted with blades or vanes. We have all swished water around the bath with our hands to get the hot or cold water circulated quickly. When we do this, our hands are acting as impellers. The steam is directed at the turbine blades, thus causing the turbine wheel to revolve. This in turn rotates the impellers. As they rotate, they draw the two propellants from the tanks and push them along pipes towards the combustion chamber. One of the impellers pumps the oxidant, while the other pumps the fuel. Great care must be taken to ensure that the two fluids do not come in contact with each other in the pumps. Otherwise, there could be an explosion and the whole rocket would be destroyed. Rockets consume vast quantities of propellants at an enormous rate, so the pump impellers must be capable of rotating at very high speeds to keep the supply flowing. And here we have a Rocketdyne FI, America's largest liquid-propelled engine. At least it was when this book was written. Valves and injectors. Valves are inserted at various points throughout the rocket's propellant system to control the flow of fluid from the tanks to the pumps and then on to the combustion chamber. They also regulate the movement of the steam which operates the turbine pump. Besides this, they are used to obtain the correct direction and quantity of flow of the liquids which pass through them. They open to allow the fluid, steam, or whatever it is to pass along the pipe, and close automatically when the required amount has gone through. The incorrect functioning of any one of the many valves could cause the complete destruction of the rocket. Injectors are the last items in the rocket's propellant system. They are fitted to the combustion chamber casing and have very fine nozzles which protrude into the interior of the chamber. The oxidant and fuel are fed into separate injectors, and as they are forced through the nozzles, the fluids are converted into a fine spray of tiny droplets. If you have ever used one of the many household atomizers and seen the fine misty spray that comes out of the small hole at the top, you will have a good idea of the effect produced by the injector nozzles in a rocket. Rocket injectors have to be designed so that the atomizing and mixing of the oxidant with the fuel in the combustion chamber are as complete as possible and produce a vapour mixture that will burn with maximum efficiency. combustion chamber. Igniters are used for this purpose. There are various types in use, one of which is the spark plug type, as in the motor car. This is mainly used for small rocket motors. Then there is the firework type, rather like a Catherine wheel mounted on a stick attached to the launching platform. Another kind of igniter is in the form of a miniature combustion chamber connected to the main chamber. In this, the fuel-oxygen mixture is ignited by a spark, and the resulting explosion ignites the bulk of the mixture in the main combustion chamber. And here we have a Beaumark ramjet, a surface-to-air missile with 2 rocket booster units. Cooling the combustion chamber. It is difficult for us to appreciate the great heat that is generated in a combustion chamber when the propellant mixture is being burnt. The temperature of boiling water is 100 degrees centigrade, and we normally consider this to be quite hot. But the combustion chamber of a rocket can reach as much as 3,000 degrees centigrade, or nearly 5,500 degrees Fahrenheit at the point of burning. This intense heat creates problems for rocket designers because the chamber has to be made of metal, and this has to be as thin as possible to save weight. As no known metals will stand anything like 3,000 degrees centigrade without melting, some means of cooling the combustion chamber wall must be found, otherwise it would simply melt away and disappear. Various cooling systems have been used, but the most efficient method employs a double wall all round the chamber, with a space between the 2 layers of metal. A cooling liquid is then introduced and circulated within the space to absorb some of the heat of the inner wall, which is in direct contact with the burning gases. The system operates in the same way as the water jackets in a car engine. See how it works, the motor car? We will. The cooling fluid is nearly always the fuel, which is circulated as the coolant before then being injected into the combustion chamber and burnt. This double wall system is known as regenerative cooling. And here we have a Saturn rocket under construction. How a rocket motor works. So far we have dealt with the principles of rocket operation and the various components which go to make up the complete rocket motor. In this chapter we will see how each individual part does its job and how the whole firing operation is started and made to function continuously. 1. The valves controlling the flow of the fuel and oxidant from the tanks are opened, and the 2 liquids begin to flow downward through the connecting pipes. They flow freely under the natural force of gravity through other open valves, leading to the pumps and injectors, and then pass to the combustion This is Kate at the Library of Whispers, and welcome to my second part reading of How It Works, The Rocket, a Ladybird book. So, let us see where we were up to. I have a bookmark, which I'll move to that side. Let's begin. Different kinds of rockets. In this great and exciting age of space, it is very natural to think of a rocket only as a vehicle which carries the astronauts up through the atmosphere and sends them in their spacecraft, hurtling towards the moon at about 25,000 miles an hour. This is the rocket's most glamorous and most exciting role. But in considering the rocket as a whole, we must not forget its many other functions. First, of course, there are the little rockets, which adults and children enjoy launching every year on November the 5th, Guy Fawkes Night. This is a far cry from sending men into space, but the toy rocket was the start of the whole business. Rockets such as these use a small quantity of solid fuel, which is ignited by lighting the blue touch paper at the lower end. The fuel burns very quickly, and in doing so creates a downward pressure which sends the rocket surging into the air. A stick attached to the fuel container is simply to give the rocket directional stability and prevent it from toppling over and flying off in the wrong direction. Some aircraft are fitted with booster rockets. These help fighter aircraft to get off the ground quickly and boost their rate of climb so that they reach their operational height in as short a time as possible. They also assist heavily laden aircraft to take off from airports with short runways and aircraft at relatively high altitudes, where the lift from the air is reduced. Now on this side of this page we have a picture of an F-104G Starfighter, an aircraft which is assisted on takeoff by a solid A truck weighing 2 tons will carry 3 tons of goods, and all other forms of transport will carry a high percentage of payload in proportion to their own weight. But a space rocket is usually 30 to 40 times as heavy at launching as the payload it carries. This is chiefly due to the tremendous amount of propellant it has to take with it to keep the motors working. Of course, the further it goes, the lighter it becomes as the propellant is progressively used up. Now this is a USAF manned orbital laboratory. The forces of gravity. Having now discovered how a rocket works and what it is for, we can go on to other aspects of rocket operation. So let us consider some of the outside forces that must be overcome before we can leave the ground and get into space. Why do things normally stay on the ground anyway? When we fall down, why do we fall down? If you throw a ball into the air, it always comes back to Earth. Why? The answer is because of the force of gravity. We stay on the ground because the Earth's gravity holds us down. We fall down because the Earth's gravity pulls us down. The same applies to the ball. It does not just drop back to Earth, it is pulled back by gravity. All bodies have gravitational pull. The greater the mass, or amount of material in the body, the greater the pull. Because the Earth is so much more massive than anything on it, everything else is pulled towards the Earth's centre. We fall down because we cannot pull the Earth up. There are 2 ways of overcoming gravity, at least for a time: by exerting an upward force greater than the force of gravity, lifting a ball into the air by speed. The harder you throw the ball, the faster it goes, and the greater the height it will reach. Resistance caused by the Earth's atmosphere is another force acting against a rocket. The efficiency of a rocket is greatly increased in the absence of atmosphere. So here we have how the pull of gravity decreases with distance from the Earth's centre. Escaping from the Earth. The Earth's gravitational pull is something we live with all the time. We take it for granted and hardly ever think about it, but it is a most important factor in rocket operation and must be overcome if we are to get anywhere in space or off the ground at all. The example of the ball, already given, holds the secret. The harder the ball is thrown, the faster and higher it will go. The secret then is speed. If we could throw the ball hard enough, it would go up and up forever and never come down. The speed at which it would have to be thrown to do this is known as escape velocity. Of course, we cannot throw a ball hard enough because the speed required to escape completely from the Earth's gravity is 7 miles per second, or over 25,000 miles per hour. Once escape velocity has been reached by a spacecraft, no further power is needed. A rocket aimed at the moon, for instance, will coast resistance caused by the atmosphere are too strong. Scientists have therefore devised a method of attaching 2 or 3 rockets together, one above the other, and these are known as step rockets. What happens is this: the bottom rocket carries the other 2 plus the payload and provides the power for the first stage of the flight. When its propellant is exhausted, the motor of the second rocket is started, and the first rocket separates and falls away to get rid of its now useless weight. This means that the second stage starts with the advantage of speed and height provided by the first. When the propellant of the second rocket is used up, the third rocket's motor starts and the second stage separates. We are now left with 1 rocket plus payload, its speed and height boosted by stages 1 and 2. By the time the propellant in stage 3 is exhausted, escape velocity has been reached, and the payload is in a condition of free fall and can orbit or go on into outer space, to the moon if desired, without any further assistance. In the illustration, the second stage propellants are shown as being forced into the combustion chamber by the use of compressed gas, instead of by pumps as used for the first stage. The third stage is shown as a solid propellant rocket. Problems of the step rocket. On page 32, dealing with the payload, it was said that rockets could be 30 to 40 times heavier than the payload they lift off the ground. This applies mainly to step rockets, in which the first stage lifts not only the final payload, but stages 2 and 3 as well. And of course, each rocket can only be used once. If we take the mighty Saturn V rocket, for example, we find that at launching, a weight of nearly 3,000 tons is required to place a 100-ton payload into an orbit around the Earth, send 45 tons to the Moon, or 35 tons to a planet. For single-stage rockets, the ratio is not so high. Another problem is to secure the various stages together. The fixing bolts have to be strong enough to hold the system together and resist the stresses, strains and vibrations set up during flight. They must also be capable of being broken when required, so that the stages can separate. Separation itself is a problem. It has to be exactly timed to coincide with the using up of the propellant in one rocket and the firing the motor in the next. One method of separating one rocket from another is to use hollow fixing bolts. A small explosive charge is put into the hollow bolts, and at the right time, the charges are set off by means of an electric signal. This shatters the bolts and allows the spent rocket to fall away. And the image is how fixing bolts of a step rocket are separated. Into orbit around the Earth. to the ground. Slow down the swinging movement and the weight will fall. This shows again that given enough speed, the force of gravity can be beaten. A speed of 25,000 miles per hour is required to escape from the Earth altogether, but 18,000 miles per hour is sufficient to maintain an orbital path at a height of 200 miles, for here the orbit of the satellite is curved to the same extent as the Earth's surface, and the satellite is, in effect, falls round the Earth. The higher we go, the less speed is required as the force of gravity becomes weaker. This picture demonstrates going into orbit. Movement in space. Even with today's expert and precise methods of launching, a rocket or space vehicle could still go off course. It is therefore necessary is a radio telescope? Messages from space. Each artificial satellite is placed in orbit for a specific purpose. Sometimes this is purely scientific, such as measuring cosmic rays from outer space or radiation from the sun, or observing the stars above the Earth's obscuring atmosphere. Other satellites have some practical everyday purpose, such as help in navigation, radio and TV, relay, mapping the Earth, or in studying the Earth's weather. The transmission of information from satellite to Earth is done by a system known as telemetry. It involves the use of a special kind of radio transmitter using radio waves in the VHF, very high frequency, UHF, ultra high frequency, or SHF, super high frequency ranges. Normal radio waves are not able to penetrate the Earth's atmosphere, but are absorbed or reflected back to the transmitter by the ionosphere, a layer of ionized gases which lay between 30 and 70 miles above the Earth's surface. It requires radio waves of very great penetrating power to get through this barrier. Power for the satellite's telemetry and other instruments is often provided by solar cells. These make use of the fact that sunlight falling on special plates made of silicon material generates an electric current, whereas small electrical storage batteries become exhausted very quickly. Solar cells can operate for a long time, and so greatly prolong the useful life of the satellite and the amount of information it can transmit. This is the Telstar satellite. The end of the beginning. No book on rockets and space travel can ever be finished. In past centuries, man has explored the Earth and has found much to wonder at. The moon, the planets and the stars have been studied from the ground, and a vast amount of information has been gathered, some of it right and, as it turns out, some of it wrong. The study of space from space is our latest adventure. A great deal has been learned in a few short years, but we are still only scratching at the door that will one day open and lead us to the conquest of the universe. This may lie centuries ahead, but it will surely come. All these high adventures will depend on the rocket for their beginnings. Propellants will undoubtedly change and be made more efficient. Atomic energy or electrical propulsion may well be used, but until such time as we can use solar energy as a means of propulsion, the general principles of rocketry will continue to apply. Radio signals to funnel radio signals from outer space into the tiny central aerial is 250 feet in diameter. Now, this book was published in 1961 by Wills and Hepworth Limited, Loughborough, printed in England. So on this side we have this lovely image. This is Caxton and his printing press. So let's read about what they say. The printing press. This book is printed. Thousands of children have a copy, and the words and pictures in each are exactly the same. But there was a time when every book had to be written by hand, and every picture drawn and painted. If you think for a moment, you will understand what a tremendous difference the invention of printing has made to the world. Printing was invented by a German, Johann Gutenberg. He printed the Bible in 1456. They knew about printing 1,000 years ago in China, but before Gutenberg it was only done by cutting out all the letters on a page on one block of wood. Quick printing began when Gutenberg had the idea of cutting letters on small blocks of metal, which could be used again and again, fitted into a frame. This is called movable type. The art of printing spread quickly. The first English printer was William Caxton, who set up his printing press in Westminster in 1476. Caxton was the first to print books in his own language. Before him, all printed books had been in Latin. Caxton translated foreign books into English, and he also printed the books of English authors, including the great poet Chaucer, and so helped to form the English language. In 15 years, Caxton printed more than 100 different books. And in the image we see Galileo and his telescope. The telescope. When the Italian Galileo was a boy, his parents did not know whether he would be a musician, an artist, or a scientist, for he was clever at everything. He had an inquiring mind. He always wanted to know how and why, and he became one of the great scientists of the world. He was professor of mathematics at Padua University in 1609 when he heard about a wonderful invention made in Holland. It was a tube with two lenses in it, and when you looked through the tube, objects seemed to be nearer and larger. Galileo did not see one of these instruments, but he at once began thinking about the idea, and he made one for himself. When he looked through it, things seemed to be 3 times as close. The new invention was called the telescope, from the Greek words far and see. Galileo devoted his time and his great scientific knowledge to making stronger ones. He learned how to grind and polish glass to make lenses, and he worked hard until he made telescopes which magnified 8 times and eventually 33 times. Galileo was richly rewarded for his work by his government, and his powerful telescopes were eagerly bought all over Europe. He used his telescope to study the heavens, and he discovered the mountains on the moon, the spots on the sun, the satellites of Jupiter, and showed that the Milky Way was a collection of millions of stars. And in this picture we see finding a ship's position in the days of sail. very special kind of watch was needed. The problem was solved by another Englishman, John Harrison. He spent many years making a very accurate watch called a chronometer. In 1761, he sent his son on a 6 weeks voyage to test his fourth watch. When he arrived in Jamaica, the watch was only 5 seconds wrong. Harrison was awarded a prize of £20,000 by the government. With a chronometer to tell the true Greenwich time, seamen could use the sextant to work out their exact position at sea. Now here we have John Hargreaves gets his great idea: spinning and weaving. Have you ever thought that cotton is made from fluffy plants and wool from the coats of sheep? For thousands of years mankind has made thread for weaving into cloth from short pieces of wool, flax, cotton and other things, teased apart and spun together into thread. Spinning was always done by hand with a spinning wheel until in 1764 a Lancashire weaver named James Hargreaves made a famous invention. The legend is that he thought of it when he knocked over his wife's spinning wheel and saw the wheel spin round. His idea was to make a machine which would spin several threads at once. He worked hard at the problem and made a machine which spun 8 threads and then 26. It was called the spinning jenny. 3 other inventions followed within 20 years, which together were to make Britain a great industrial country. 4 years after Hargreaves invented this spinning jenny, Sir Richard Arkwright made a spinning machine driven by power, first by a horse and then by a water wheel. The 2 inventions were combined by Samuel Crompton in a machine called the spinning mule. The 4th invention was made by the Reverend Edmund Cartwright in 1785. This was the power loom. Until then, cloth was woven on hand looms, but Cartwright invented a way to do it with machinery. Factories were built and the new machines installed. Britain sold cloth to foreign countries and soon became the richest country in the world. And here we have James Watt and an early steam engine. The steam engine. One day, in 1763, a young Scotsman named James Watt began to mend a model engine. It was a model of a steam engine which had been invented 60 years before and was used to pump water out of coal mines. As James Watt mended the model, he made a great decision. He would try to invent a better kind of steam engine. He studied steam and made many experiments, and at last he built his first full-size steam engine. To his joy it worked, and produced more power for its size than the old type, and used less fuel. Watt devoted all his time and energy to steam engines, and went into partnership with a Birmingham manufacturer, Matthew Bolton. Soon Bolton and Watt became famous for their engines. Good though their steam engines were, they only drove a shaft backwards and forwards for pumping. Then Watt made his second and very important invention. It was a great day when he patented it in 1781. The new idea was a steam engine which drove a wheel round. It gave the world a new source of power. Steam engines could be used to drive wheels, the wheels of locomotives, the paddles of ships, the machinery in factories. It was the Edison's most famous engine was the rocket, which his son Robert helped to design. In 1829, a prize of £500 was offered to the designer of the best locomotive. 5 engines took part in the tests, and the rocket proved to be the best in every way. It astonished everyone by hauling a train at the wonderful speed of 36 miles an hour. With Robert, George Stephenson became the leading railway engineer in the world, both for building engines and making railways. Engines had jolly names in those days, and one very famous one was called Puffing Billy. And here we have an early steamship with paddle wheels. The steamship. When James Watt perfected the steam engine, men naturally turned their thoughts to using it for ships. One of the earliest successful steamships was built by an American, Robert Fulton, in 1807. She was called Clermont, and she was driven with paddle wheels on each side, but she had masts and sails as well. Her first voyage was up the Hudson River from New York to Albany, and her average speed was just over 4.5 miles an hour. Sailors were naturally scornful of a ship driven by a steam engine. Sailing ships were graceful, and with a good wind they were fast. The early steamships were neither graceful nor fast, but the men who believed in them persevered. The first ship to cross the Atlantic entirely under steam was the Sirius in 1838. More and more steamships were built, all with paddle wheels and with masts so that they could use their sails as well. In 1840, the Cunard Company built 4 steamships for a regular service to America. The sailors who had mocked the idea of engines in ships were even more scornful when it was known that an iron steamship was being built. Everyone knew that wood floats and iron sinks, but the new iron ships did float, and in 1844 the Great Britain was launched at Bristol. She was the largest ship in the world and was built of iron. Instead of paddle wheels, she was driven by a screw. She still had sails with 6 masts. It was the Great Britain which proved that the day of the steamship had come. And here we have the turbines of a modern ship. The steam turbine. The steam engine uses the force of steam to drive a piston in a cylinder. The force of steam is used in another type of engine, the steam turbine. The basic idea is quite simple. It is rather like a windmill, where the wind blows on the vanes and turns them round to drive a shaft. In the steam turbine, jets of steam expand between the vanes on a shaft and those on the casing and spin it round, providing smooth and constant power. The inventor was Sir Charles Parsons. After studying at Cambridge University, he joined an engineering firm and devoted his time to inventing the steam turbine. As with so many other new ideas, it had been studied by others, but without success. Parsons refused to be discouraged by failures, and in 1884 his perseverance was rewarded. He made a steam turbine which worked. The idea was improved by Parsons and other engineers, and the machines were perfected. In 1890, steam turbines began to be installed in electric power stations. A turbine was fitted to a ship in 1897, and when it was tested, it start with the Davy safety lamp. I hope you enjoyed the little reading of this gorgeous Ladybird book. This has been Kate at the Library Whispers saying, I shall see you very soon. Bye bye for now. Bye bye. Hello everybody, this is Kate at the Library of Whispers, and today I am going to read the second part of this Ladybird Achievements book on great inventions. So, bookmark the page right here. We will start with the Davy safety lamp. When coal miners are working deep underground, there is a great danger of disaster if a gas called fire damp is allowed to collect in the narrow galleries. If a naked flame or a spark comes into contact with a concentration of fire damp, it can explode. Today, mines are scientifically ventilated and equipped with electric light, but even with these precautions, terrible accidents occur. In the old days, they tried all manner of methods to give a coal miner light without risking an explosion. They even tried using a bowl of decaying fish so that the miner could see from the faint phosphorescence given off by the fish skins. They tried to bring daylight down into the mine by using mirrors as reflectors. Another idea was a steel wheel rotating against flint to send off a shower of sparks. The problem was solved in 1815 by Sir Humphrey Davy. He was not connected with coal mining, but he was a very clever chemist. He had started life as a surgeon's apprentice in Penzance, and by his hard work and brilliant brain he rose to become a Fellow of the Royal Society, and he was knighted for his discoveries. Sir Humphrey Davy's invention was simple. He designed an oil lamp with a fine gauze round the flame so that the heat was prevented by the gauze from getting out to ignite dangerous fire damp. It was called the Davy safety lamp, and until electric lighting was introduced into coal mines, it was always used. It prevented accidents and saved countless lives. And here we have a picture of old-time coal miner with a Davy safety lamp. The sewing machine. Imagine that you are watching your mother sewing carefully by hand, and that you have the idea of inventing a machine for sewing. How would you set about it? If you watch a modern sewing machine and see how fast the needle flashes up and down, and how fast and even the sewing comes out, you realise what a lot of thinking the inventors had to do. In 1790, an Englishman patented the idea for a sewing machine, but it was never made. No one knew anything about it until 100 years later. Meanwhile, in 1830, a Frenchman, Thimonier, invented a sewing machine which worked. It was made mainly of wood. Thimonier was a poor man, and he won neither fame nor fortune in his life. Indeed, he was nearly murdered. In 1840, 80 of his machines were being used in Paris to make army uniforms when an ignorant mob attacked the place. They thought that the machines would put them out of work, so they smashed them all and attacked the unfortunate inventor as well. Many other inventors were working on the problem, and about 1832, an American named Elias Howe had a brilliant idea. He devised a needle with the eye at the pointed instead of at the blunt end, and that made all the difference to sewing machines. A great number of patents were taken out in the years that followed, as one inventor after another thought of improvements, and so the modern sewing machine came into being. Think of the time that invention has saved. And in this picture we have the Paris mob wrecking the first sewing machines. Electricity. Man has known of the existence of a mysterious force called electricity since ancient days. There is even a mention of it in the year 600 BC, but it is only in the past 150 years that we have discovered how to use electricity. The first important discoveries were made by an Italian scientist, Volta. In 1800, he made batteries which gave out electricity, but it was a British scientist, Michael Faraday, who made the greatest discovery. Faraday was the son of a Yorkshire blacksmith who moved to London, where young Michael began his working life as errand boy to a bookbinder. But his one interest was science, and in 1812, when he was 21, he wrote to the famous Sir Humphrey Davy and was made his assistant. He was so successful that when Sir Humphrey died, Faraday succeeded him as professor at the Royal Institution. Faraday made a number of important discoveries in chemistry, but his greatest work was on electricity. He studied the work of previous scientists and spent 20 years experimenting to find out how to make electricity. It was in 1831 that he had his greatest success. With simple apparatus consisting of a magnet, a copper disc and wire, he made or induced an electric current. It meant that this magic force could at last be produced at will. It was the beginning of the dynamo or electric generator, which produces the electricity used for power and light throughout the modern world. And in this picture we see Faraday in his laboratory. Electric light. Michael Faraday discovered how to make electricity by mechanical means, and he and other scientists developed the dynamo, which provided electric current to drive machines, but electricity was not used for lighting until 50 years afterwards. Two men made the discovery of how to use electricity for light at about the same time. One was an Englishman and the other an American. The Englishman was Sir Joseph Swan, an electrical engineer and chemist who studied the problem for 20 years before he hit upon a solution. The American was the famous inventor Thomas Edison, who made a number of important inventions. Both Swan and Edison discovered in different ways that if a current of electricity is passed through a fine thread of filament or carbon, it will glow white hot and give a strong light. The thread of carbon was enclosed in a glass bulb from which the air had been extracted, making a vacuum. During the following years, was a Scotsman, Clerk Maxwell, who made wireless possible. He was a mathematician, and in 1863 he worked out entirely by mathematics that wireless communication must be possible. The next step was taken 25 years later, when a German, Heinrich Hertz, made experiments which proved that Maxwell's theory was true. Other scientists worked on the problem, and in 1896 Guglielmo Marconi, a 20-year-old Italian, discovered how to send signals by wireless. He made many experiments, and in 1901 he succeeded in sending signals across the Atlantic to America. This wonderful invention was quickly adopted, especially at sea. Ships could send and receive messages and were ever ready in an emergency to send the distress signal SOS. The next problem was to transmit the human voice by wireless. Clever men all over the world made countless experiments, and gradually the problems were solved. The most important part of the invention was the wireless valve. Transmitters and receivers were improved, and it became possible to transmit the human voice, music, and any sounds. Wireless telephony, which we now call radio, was invented. And here we have wireless at sea, a wireless operator sending SOS. The bicycle. The bicycle first became known as a means of transport when the hobby horse was shown at an exhibition in Paris in 1818. It was a wooden frame with two wooden wheels and no pedals, and the rider pushed himself along with his feet on the ground. It was in 1839 that the first real bicycle came into being. A Scottish blacksmith fitted his hobby horse with pedals, rather like sportsman, the Honourable Charles Rolls, went into partnership with Henry Royce, an engineer. Together they built the Rolls-Royce motor car, which has long been known as the best car in the world. Few inventions have made such a tremendous difference to everyday life as the internal combustion engine. It has altered the way of life with motor cars and motorcycles, buses, lorries and aeroplanes. And the picture shows an early motor car. The diesel engine. While Daimler, Benz and others were working out the internal combustion engine to drive their motor cars, others were trying to develop a different kind of engine. In the petrol engine, the compressed petrol gas is exploded by a spark and drives the piston in the cylinder. In the other kind of engine, air is compressed in the cylinder, becomes very hot, and when fuel oil is injected into it, it explodes without a spark to set it off. The first engine of this kind was devised by an Englishman, H. Ackroyd Stewart, in 1890. A German, Rudolf Diesel, was also working on the same idea, and although his invention was not patented until 2 years after Stewart's, the engines are named after him. Diesel had many disappointments, and once was nearly killed when an engine blew up, but in 1898 the diesel engine was shown in an exhibition in Munich and was soon taken into general use. It proved to be ideal for ships and boats, heavy lorries and motor buses. It was also used for railways, and very powerful diesel engines are now gradually taking the place of the steam locomotive. And here we see a modern diesel locomotive. The aeroplane. Man has always envied the birds, and for centuries scientists had tried to find out how to fly. It was not until the invention of the internal combustion engine, however, that flight in heavier than air machines became a practical possibility. Many people took part in the quest for the secret of flight, and in 1903 two American brothers first flew in an aeroplane. Orville and Wilbur Wright were partners in a bicycle repair business and began to make and fly gliders in 1900. In due course, they modified a motor car engine to drive a propeller and fitted it to a specially adapted biplane glider. They first flew their aeroplane on December the 17th, 1903, a great day in history. They made 2 flights each, the first of 12 seconds, the second and third longer, and the fourth lasted nearly a minute, which covered 852 feet. They kept on improving their machines until in 1908 Wilbur flew for an hour and 20 minutes. Other enthusiasts made use of the knowledge gained by the first flights, and aeroplanes were made and flown in England, France and America. In 1909 It was to do away with propellers and to fly the aeroplane much faster with a jet engine. He worked at his idea, and when he was an officer and studying at Cambridge in 1935, he patented his invention of the jet engine. The jet engine works on the same principle as a rocket. Air is drawn into the front of the engine and is burned with paraffin. The gas so formed expands violently and rushes out of the back of the engine in a jet and propels the aeroplane forward with great power. Other engineers were working on the same idea, especially in Germany and Italy, but Whittle did not know this. He formed a company to make jet engines, but no one took much notice until war broke out in 1939. That made all the difference. The government took up the idea, and the jet engine was developed urgently. Before the end of the war, fighters were flying at high speeds, powered by jet engines. After the war, jet engines were developed further. Jet-powered aeroplanes have flown at more than 1,500 miles an hour, and giant jet-engined airliners fly at speeds never dreamt of by the pioneers of flying 50 years ago. And here is a jet engine at speed. The camera. Perhaps you have a camera. You will certainly have had your photograph taken and wondered at the magic of the camera. Many people had a hand in inventing photography, but the credit is given to an Englishman, William Fox Talbot. He took a photograph in 1835. Many other inventors worked at the idea, and the most important was the Frenchman, Daguerre. Fox Talbot spread the chemicals with the pictures on paper. Daguerre went one better by using copper plates covered with silver. In 1851, glass plates were used for the first time, and in 1884, film was made of celluloid. The next development was the moving picture, and here again a number of people were concerned. An Englishman, William Freese Green, is recognised as the father of the moving picture, though important work was done by an American, Edison, and a Frenchman, Lumiere. For moving pictures, a long strip of celluloid is used, which unwinds inside the camera, while the shutter opens and shuts rapidly. The series of pictures shown through a projector shows the movement. The first public showing of a film was in London in 1890. Many improvements were made by inventors, mostly in America. At first, only very short films were made, but in 1903, a complete, exciting story was filmed, so gradually the cinema industry was born. This is making a film. Television. In 1922, a Scotsman named John Ladybird assembled some rather odd apparatus in his bedroom in a Hastings lodging house. He had his washstand for his workbench, a tea chest, an electric motor from a junk shop, 2 lenses from cycle lamps, a torch, parts of a dismantled army radio, and some wire. He also had string, glue, and sealing wax. Bird had gone to live in Hastings because he was ill. He was poor and he had no job, yet he had set himself the task of inventing an apparatus which would send pictures by radio, television. It was a problem many people were trying to solve. Bird was not daunted by his many handicaps, and he persevered stubbornly with his meagre materials. For 2 years he had no success, but he kept at it, and at last he was rewarded. One day he transmitted the picture of a Maltese cross over a distance received